she's so floppy.
Okay, guys. So, so we're gonna move on to 76. So this section is the calculator section. So some of these will require your graphing calculator. Not all of them, though. So let's have a look at this first one here. They say the graph of a differentiable function f is shown in the figure below. Which of the following is true? Well, basically, what you have to ask is what is the derivative of this function at each of these points, right? So you're being asked to compare f prime of -2, f prime of 0, and f prime of 3. Well, the values of those expressions are just going to be the slope of the tangent line at the given point. So f prime of -2, you know, is going to be the slope of the tangent line right here at -2. I don't really know exactly what that value is, but it's certainly a positive slope, so that's definitely a positive number. F prime of 0 is, well, it appears to be flat, so it appears to be something like 0, right? The tangent line looks horizontal more or less. And then finally, f prime of 3, the slope of the tangent line, whatever it is, it's negative, right? So since this is negative, and this is about 0, and this is certainly positive, the order is the slope of the tangent line here is the smallest, so f prime of 3 should be lowest. That brings it down to C or D, and then this guy should be in the middle. That means it's got to be choice D. Okay, so looking at 77, they tell you that you've got this antiderivative. They tell you that h of x is an antiderivative for this function. Let me switch to my notebook here. So 77, h of x is an antiderivative of the function x to the third plus sine x over x squared plus 2, and they tell us that h of 5 is equal to pi, and they are asking what is h of 2. Well, the way to think about this is basically, you know, we know that h of 5 is going to be equal to h of 2 plus the integral of h prime of x dx from 2 to 5. As far as why this formula holds, there's several ways of thinking of it. One way of noting, I mean, we did problems like this in class many times. One way of understanding it is that it's really just using the fundamental theorem of calculus. If you subtract h of 2 from both sides, you obtain the formula this integral is equal to h of 5 minus h of 2. Or you can view this as sort of like a net change. This is sometimes what I call the later value of h. This thing here is the earlier value. And then this, integrating the derivative of the function, gives you the net change. And so we sort of talked about this in class a little while back, a couple of months ago maybe, that the later value is going to be equal to the earlier value plus the net change in the function from 2 to 5, which is what integrating the derivative gives you. Now, some of this information we already know. We know that h of 5 is pi. And then this thing here, so let's see. So pi is equal to h of 2, which is the thing we're trying to find, plus, and then we need to think about, you know, what is this expression here? Well, we can compute it using our calculator because h prime is the derivative of h. Well, we know that h is an antiderivative of this expression here, so therefore h prime must actually be this expression here. So in other words, we have pi is equal to h of 2 plus the integral from 2 to 5 of x to the third plus sine of x over x squared plus 2 dx. We can compute this thing using our calculator and then subtract it from both sides to obtain the value of h of 2, so I'm going to go ahead and do that. I need to put that function into my calculator first of all. So let's see. So x to the third plus sine of x all over quantity x squared plus 2. Okay, so that's my function there. Because this thing involves a trig function, I'm going to make sure that I'm in radians. Oh, I'm not. How embarrassing. All right. Oops. So mode. There we go. I'm in radians now. And I'm just going to take a look at the window that I'm on. Looks like I'm on the standard window right now. So I'm going to go to the graph. Here's this function. And we just need to compute the area under the curve from 2 to 5, which is done by going into the calc option. So I hit second and then calc, and I go down to the integral symbol here, hit enter. Lower limit is 2, upper limit is 5. Okay, so there's the area. So that's looks like 9.008 or something. So this is 9.008. So therefore I find that pi minus 9.008 is equal to h of 2, which gives me something like, it's more like 0.99, it's more like 9.008257. I'll throw in some more decimal places there just in case. So pi take away 9.008257. Okay, so it's like negative 5.866. So is that one of the options? Yeah, it looks like choice B is the one. Maybe just a quick note, if this whole thing threw you for a loop, like where in the world I got this formula, it's really just the fundamental theorem of calculus, right? If you have an integral of, say, the derivative of some function, say f prime, from a to b, like you know how to compute this, right? You take an antiderivative and then you evaluate it at the limits of the integral. Well, if you're integrating a derivative, if you're integrating f prime, then surely an antiderivative of this function, an antiderivative of f prime, is just f itself. So the integral of this function, take an antiderivative of this, which is just f itself, and evaluate it from a to b. So that tells us that the integral from a to b, f prime of x dx, is equal to f of b minus f of a. And that's basically the formula that I'm using here. I'm sort of saying, if you solve this for f of b, then I obtain f of b is equal to f of a plus integral from a to b f prime of x dx. That's the formula that I was using a moment ago. It basically says that the later value of the function is equal to the earlier value of the function plus the integral of the derivative. That's the principle that I was using there. Okay, let's move on to 78. They tell us in number 78 that we have a continuous function and it's positive and it has domain x bigger than 0. So f is continuous, it's positive, and the domain is x is bigger than 0. They tell us that we have asymptotes at, looks like we have both the horizontal and a vertical. So we have a vertical asymptote at x equals 0, that's a vertical line, and a horizontal asymptote at y equals 2. And they ask us which of the following have to be true. Let's just think about each of these in turn. So let's have a look. So, sorry for the weird appearance of my iPad on the projector or the document camera. So, the fact that we have a vertical asymptote at x equals 0 means that the value of the function has to go to infinity as you approach 0. Now, normally that could occur as you approach 0 from the left or the right, but because the domain of the function is restricted to x being positive, we're only permitted to approach 0 from the right. So the fact that there's a vertical asymptote at x equals 0 and the domain of the function is for x positive means that the limit as x approaches 0 from the right has to be some kind of infinity. It could be positive infinity or could be negative infinity, although we're also told that the function is positive, which means actually it has to go to positive infinity. You know, if you want a picture of what I'm saying here, I'm just saying that, you know, since the function has to be positive and it's only defined for x bigger than 0, and we have a vertical asymptote at x equals 0, it's clear that, yeah, the limit as x approaches 0 from the right has to be infinity. So that's the logic that I'm using there. So back to the question here. So right away we can say that b doesn't make any sense, right? Limit as x approaches 0 is equal to 2. That certainly doesn't make any sense. Now, what about the horizontal asymptote, like the y equals 2? What does that tell us in terms of limits? Well, horizontal asymptotes are associated with limits at infinity. And the reason for that, the explanation is just that if you have, you know, a function and you have some horizontal asymptote, right? Like let's say it's doing something crazy here, but then gradually it just approaches this horizontal asymptote. If you think about what that means in terms of limits, if this is my function f, it's really saying that the limit as x approaches infinity, let's say this y value is 2 or something, it's really saying the limit as x approaches infinity of this function is 2, right? Because if you have a horizontal asymptote, that's just saying that as you go way out to the right on the x-axis, the value of the function gradually approaches more and more closely 2. Well, that's exactly what this limit is saying. As x becomes very large, the function's approaching 2. So going back to the problem here, that's the other limit that has to be true, and that occurs in in C and D, but we know also that we need this limit as x goes to 0 from the right as well, so it's got to be C. Okay. All right, so 79 is sort of an interesting question. It's an interpretation problem. It says a file is downloaded to a computer at a rate modeled by the differentiable function f of t, where t is the time in seconds since the start of the download, and f of t is measured in megabits per second. Which of the following is the best interpretation of f prime of 5 equals 2.8? Right away, if you see f prime of 5 equals something, what they're doing is they're telling you the rate at which the function is changing at t equals 5, right? Now, the function f itself, it represents what? It represents at a rate. F itself, somewhat confusingly, itself is already a rate of change. It's maybe easy to overlook that. But if you read the question carefully, it says a file is downloaded to a computer at a rate modeled by the differentiable function f of t. So f of t, the original function, not the derivative, but the original function itself already models a rate of change. So now if you differentiate that function, you will get the rate at which the rate is changing. A little bit like acceleration, okay? If f were position, that, you know, or if f were velocity, then f prime would be acceleration. So we're looking for some kind of statement about the rate of downloading increasing by 2.8. Right? So A says the rate at which the file is downloaded to the computer is 2.8 megabits per second. You know, that's actually not right, right? I mean, that's 2.8 megabits per second. That would be like a value of the original function f. B says the rate at which the file is downloaded to the computer is increasing at a rate of 2.8 megabits per second. That's the acceleration flavor thing that I was talking about. So it's definitely B. Okay. 80 is a more conventional question. It says it wants to know where the following function is concave up. they tell us that f prime is equal to x to the fourth minus 6x squared minus 8x plus 3. Concave up simply means one way of interpreting the second derivative is, one way of interpreting concavity is that it corresponds to the sign of the second derivative. So concave up simply means the second derivative is positive. So let's find the second derivative by differentiating this function. I get 4x to the third minus 12x minus 8. And I want to know, where is this function positive? Well, you can set up a number line, certainly, although in order to do so, you're going to have to solve a cubic equation, which maybe you could do. This can be simplified. All of the coefficients are divisible by 4. You get x to the third minus 3x minus 2 is equal to 0. If you really remember how to factor cubic polynomials from algebra 2 or whatever, well, I mean, bless you. But like most people don't. The good news is that you can use your calculator, right? You want to know you simply want to know where is the second derivative positive. So just punch that thing into your calculator and look at the graph, right? So let's go ahead and do that. So I'm going to go to y equals, I'm going to punch that second derivative function into my calculator. So that's 4x to the third minus 12x minus 8. And I'm just going to graph this thing. Okay, so I can see that it looks like there could be some little point here where it's positive, or maybe it just nicks the x-axis there. It's not entirely clear. I think maybe I'll zoom in just to get a better picture. Okay. Right, so I can see now that the graph doesn't actually go into doesn't actually cross the x-axis here. It just bounces off of it. And then it's only actually positive at this value and to the right, which is for, that x value is 2. So 2 to positive infinity is where the second derivative is positive. That's where it's going to be concave up, so 2 to positive infinity. Okay, now we have some very pretty pictures. 81 says the graph of the function f is shown above for x between negative and positive 2, which of the following could be the graph of an antiderivative of f. So we're asking, is this function the antiderivative of this one, or is this one the antiderivative of this one? It's a bit hard to think of it that way. The better way to think of this is the following. Consider the first graph shown in A. Is it possible that the derivative of this function has a graph which looks like this? Right? That's the kind of question that we're accustomed to answering, right? We give you a graph and we sort of ask you, what does the graph of the derivative look like? That's a much easier question to answer. And I think it's how you should view this question. So looking at A, does the derivative of this graph here match up with this one? Well, just consider the slope of the tangent line at various points. Right here at negative 2, the slope of the tangent line is certainly very steep, very positive, so it should be a very large positive number. Is the value of this function a large positive number at negative 2? No. So we can forget about A. What about B? At negative 2, thinking about the slope of the tangent line here, the slope of the tangent line is, again, in this graph, very steeply positive. So the value of the derivative should be a very large positive number. Well, is the value of this function at negative 2 a very large positive number? Again, the answer is no. Moving on to C. In graph C, it seems that the slope of the tangent line is fairly negative at negative 2, and our graph F does have a negative value at negative 2. So that's sort of interesting. What else do we notice? Well, we notice that right here, the tangent line appears to be horizontal. So if this function up here is the derivative of this one, then this function here should be 0 at this point between -1 and 2, and it does appear to cross the x-axis at that point. So evidence is beginning to build that that this thing is the derivative of c. But we can check more points if we want to be sure. For example, C right here, what I'm noticing is it seems like there's another horizontal tangent line right here. So the slope is 0 there as well. Is the value of this function 0 at that location? I actually don't think it is. Right? Like, if this function were the derivative of this one, then since the slope of the tangent line is 0 right here, the value of this function should be 0 at that point, and it's not. It's very clearly positive. So that actually refutes C. The only thing left is D, and you can check if you want, but you'll see that it matches up. But by process of elimination, we can rule out the other ones. Okay, so let's continue with number 82. First, I wasn't completely sure that we assigned this one, but we did. So let's go ahead and do it. 82, we have a particle traveling along a straight line, pretty common situation. And the velocity function is given by 3e to the negative t over 2 times sine of 2t. And they want to know what's the total distance traveled by the particle during the time interval 0 to 2. So we want distance traveled over 0t, between 0 and 2. So the thing to remember is that when you integrate the velocity function, you don't exactly get distance traveled, you get displacement. So if I just went and integrated 0 to 2, v of t dt, that will give me the displacement, which sometimes is the same thing as distance traveled, right? If the particle never changes direction, if it's always traveling in the same direction, then displacement and distance traveled are the same. However, if the particle turns around during any point in time over this time interval, then displacement will be the wrong thing. So there's a couple ways of finding distance traveled. One is to sort of figure out where the velocity function is positive and negative. Like if it's positive here and then it's negative over here or something, then you can integrate the velocity function separately over this region and then separately over this region. Of course, when you integrate the velocity function over this second region, you'll get a negative number. And if you're interested in finding distance traveled, then you basically find the area of each of these objects, make them all positive, and add them together. But that requires figuring out like where it crosses the horizontal axis and so on. It's kind of a pain. Since we have a calculator on this section, there's actually kind of a trick that we can do. The distance traveled can be found with one single integral, even if your velocity function, crosses the horizontal axis. That is, even if your particle changes direction. The distance traveled will always be the integral, in this case from 0 to 2. If we take the integral of the absolute value of the velocity function, that will actually give us the right answer. So what I'll do is I'll integrate the absolute value of the velocity function with my calculator, and I'll just get an answer that way. So I don't even need to go to the graph of this thing necessarily. I can actually just use the integral function within the calculator and not even worry about the graph. So let's go ahead and do that. So if we go to math, and then I scroll all the way down to fn int, that's the last option there. It stands for function integrate. You can see the integral that's been set up there. I want to integrate from 0 to 2, and I want to integrate the absolute value of my function. Now, the absolute value function is accessed by going to math and then over to number, and then ABS, it's that first option there. It's absolute value. So if I hit enter, okay, now I'm just going to type my velocity function inside of here. So it's 3e. So, jeez, I am really not typing very well today. So 3 e to the negative, well, it's t, but we're going to write x. It doesn't matter what variable you use. Negative x over 2 sine of 2x, close parentheses, and yeah, and if I just hit enter, that should, oh, and I also have to tell it which variable here at the end, so I have to hit x there as well. Hit enter, it's thinking. 2.261. So hopefully that's one of the options. Yep, it's D. So yeah, so you can, if you want to sort of waste time, I guess, you could like figure out where this intersection point is and then integrate these regions separately, but you can do it with just one integral if you use the absolute value bar. So that's the way to go. All right, let's have a look at 83. 83 says there's a function and its derivative is given by f prime equals x to the third minus 8x squared plus 3 all over square root of x to the third plus 1 over the interval -1 less than x less than 9. And they ask, at what value does f, not this function, but f, the original function, attain a relative maximum? So where does f have a relative max? Well, if you think about it, relative maxima and minima occur at critical points. That's places where the first derivative is 0 or undefined. I think that we shouldn't really think too carefully about critical points of the type where this function is undefined. I'll explain why in a moment. Let's just get to, you've probably seen through the many examples we've done that when you're thinking about critical points, you know that in theory critical points come in two varieties, right? One is critical points of the type where the first derivative is 0, and the other is where the first derivative is undefined. But you've probably seen by now that critical points of the type where the first derivative is undefined are often not really useful, and so your instinct should be really to just go hunting for places where the first derivative is 0. But I will investigate the possibility that maybe the critical point we're after here is actually one at which f prime is undefined. But I'll get to that later. So first, let's just set this thing. Well, we could, I suppose, try to solve this algebraically, but there's really no need. We have a calculator, so we can just graph it. So what I'm going to do is just graph this function, and we'll look at the graph and we'll sort of ask ourselves what's happening with the original function given the graph of the derivative. So the function is x to the third minus 8 x squared plus 3 close parentheses over square root. I know this must be absolutely enthralling to watch me just tediously punch in these numbers into my calculator, but okay, so there's the function, and now I'm going to graph this thing, and we'll see what it looks like. Okay, actually right away I can tell I'm probably zoomed in too closely from the previous problem, so I'm going to go to zoom standard. That's the standard 10 by 10 window, so I can have a better picture. Remember, we're interested in the interval -1 to 9, so we should make sure that whole thing appears. So what does this graph really tell us? Remember what this is. It's a graph not of the original function f. It's a graph of the derivative of f, okay? We're interested in places, we're interested in finding where does f have a relative maximum. You might notice that there's a little relative maximum right there, and you might be tempted to say that's the point that we're after. It actually is not, because that is a relative maximum of this function, of the derivative. We are trying to find a relative maximum of the original function f. This is not the graph of f. This is the graph of f prime. So what are we looking for? We're looking for critical points, places where the first derivative is 0, right? And I see three such points, one here, and one here. And I think all three of those are within this interval. I'd have to sort of look more closely to make sure that this isn't too big, but I think they all do. So all three of these places where f prime crosses the x-axis are critical points, but we have to ask, what is the nature of these critical points? Are they local minimums, local maximums? Well, at this, let me go ahead and zoom back in so I can sort of point a bit more clearly. At this point right here, which is almost to -1, f prime switches from negative to positive. Okay, let's think about what that means. If the derivative switches from negative to positive, that means the original function switches from decreasing to increasing. That is a relative minimum. Okay. This thing, on the other hand, very promising, f prime switches from being positive to negative. If f prime switches from positive to negative, that means the original function is switching from increasing to decreasing. That's exactly what a relative maximum is all about. So this point right here, that's the important point. There's one other point, as we saw, way over here, but that's going to be another relative min, not the thing we're looking for. So this thing right here, whatever that point is. So how do we find it? Well, you can use the, go to second calc and go to intersect, right? If we go down to intersect here, enter, oh, actually, no, that's not really what I want. Not intersect. I want 0. So I go to second calc to 0. There we go. So left bound, you just want to sandwich the intersection point between the two cursors. So left bound to the left of the intercept and right bound to the right of the intercept. Hit enter. Okay, so it gives me 0.638 approximately. So is that one of the choices? Yeah, that's choice C. Okay, so that's number 83. Moving on. Let's have a look at number 84. It says the number of bacteria in a container increases at the rate of R of T bacteria per hour. So R of T is the rate of increase of the bacteria. They tell us there are 1,000 bacteria at time t equals 0. And they are asking us which of the following expressions gives the number of bacteria. So we want the number of bacteria at time t equals 3. Well, I used this formula sort of earlier, right? And I talked about it in a previous problem. I forget which one off the top of my head, but it comes directly from the fundamental theorem of calculus. Sometimes I write it like this. I say f of b is equal to f of a plus integral a to b f prime of x dx. This is like the value of the later value of f, right? The f at some later time b is equal to the earlier value of f, that's the value of f at some earlier time a, plus the integral of its derivative, which this thing here is the net change, right? If you integrate the derivative, you get the net change. So there's some, if we sort of let f of t be the amount of bacteria or number of bacteria at time t, then what we can say is that f of t, we're interested specifically in knowing the amount of bacteria, not just at some arbitrary time t, but when t is equal to 3, we're interested in what is f of 3. We can use this formula and say, oh, f of 3 is going to be f of, I'll say 0 plus the integral from 0 to 3 f prime of x dx. Or maybe I should be writing t, right? The independent variable is actually t here, so I should be calling it t. All right, well, so this is the thing that we're trying to find, right? It's the amount of bacteria at time t equals 3. F of 0, that's the amount of bacteria when t is equal to 0. We know what that is. It's 1,000. Plus, integral from 0 to 3. Now, f prime of t, what is that? It's the rate at which the bacteria, the amount of bacteria is changing, right? Which is exactly what this thing is here, right? R of t is the rate of increase of the bacteria. That's the derivative of f. So that would just be capital R of t dt. So this thing is going to give us the right expression. And sure enough, that's one of the choices. Looks like choice D. Okay, 85. The function g is continuous on the closed interval. Let me sort of jot this down. So g is continuous on the closed interval 1, 4. We know that g of 1 is equal to 5. We know that g of 4 is equal to 8. And they say of which of the following conditions, or of the following conditions, which would guarantee that there is a number c in the open interval 1 to 4 where g prime c is equal to 1. So what we're looking for is a condition, an additional assumption, which would assure us that there is a number c in the open interval 1, 4 such that g prime of c is equal to 1. Hopefully this problem seems like something that you should be using one of the theorems on, right? Like maybe it's the intermediate value theorem or the mean value theorem or something. It happens to be the mean value theorem. If you remember, the mean value theorem basically says that under certain conditions, and we'll talk about what those are in a second, under certain conditions, the average rate, so here's the mean value theorem, under certain conditions, the average rate of change over any interval you want, but let's say 1, 4, since that's the interval that we're interested in this case here. So the average rate of change of g over that interval is going to be equal to the instantaneous rate of change of g at some point inside the open interval 1, 4. So mean value theorem is kind of complicated, but in a sentence what it tells you is that the average rate of change over an interval, whatever that is, there always exists some point inside that interval at which the instantaneous rate of change, that is the derivative at that x value, is the same as the average rate of change, or average rate of change is equal to instantaneous rate of change. This c, whose existence is assured by the mean value theorem, is exactly what they're talking about here. And really what the question is asking you is, what additional hypothesis do you need in order for the mean value theorem to kick in? If you compute the average rate of change of g over 1, 4, and you can't actually do it with this information, because it would be g of 4 minus g of 1 over 4 minus 1. They tell us what g of 4 and g of 1 are, right? This is 8. This is 5. So it's 3 over 3. Yeah, you get 1. So the average rate of change over that interval is indeed 1. And if the mean value theorem were to kick in, that would tell you that yes, there's some point on the open interval at which the instantaneous rate of change, in other words, g prime, right, of c, would be equal to the average rate of change of the entire interval. So as I said, the question really just boils down to what additional hypothesis do we need in order for the mean value theorem to kick in? Well, the conditions for the mean value theorem, there's really two of them. The function needs to be continuous on the closed interval, in other words, including the boundary points, and it is, right? That's one of the assumptions made. The other condition that needs to be met is that the function needs to be differentiable on the open interval, okay? So I'm assuming that one of these choices is that the function is differentiable on on the open interval 1 to 4. Yep, That's what it is. So choice B, the function needs to be differentiable. That's the additional hypothesis needed to make the mean value theorem kick in. Okay. I'm going to try and plug in my iPad if I can, because it's kind of dying. Let's see. Well, whatever. If it dies, it dies. So let's move on to 86. It says, the twice differentiable functions f, g, and h have second derivatives given above. Which of the functions f, g, and h have a graph with exactly 2 points of inflection? Okay, well, they tell you that f double prime is equal to x times x minus 1 squared. Well, no reason to really copy that. I can just gesture to it on the iPad. So here are the three functions, and we want to know which of these functions have exactly 2 points of inflection. Well, an inflection point is a place where the concavity changes. Okay, and one way of talking about concavity is to think about the sign of the second derivative. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. So a point of inflection is a place where the second derivative changes sign. Now you can imagine making a number line for each of these three functions. You're going to get, a bunch of zeros from each of these factors. You're going to get a 0 from that factor, a 0 from this one, and a 0 from this one as well. But then you're going to have to really do a sign analysis to sort of determine, to really determine which of them actually changes sign at the given point. What I just noticed here is that they're not really in factored form. There's like a +1 there, and then a -1 here. It's pretty easy to analyze the points of inflection of this first function because it's in factored form. We know exactly where this function is going to be equal to 0. It's going to be equal to 0 at x, at 1, and at -2. And you can do a full sign analysis if you want, but if you remember your algebra 2, whether or not the function changes sign at a 0 depends upon whether the multiplicity of the root is even or odd. This x, since it's being raised to a 1, that's an odd multiplicity, so the function will change sign at the root associated with that factor. So in other words, there is a point of inflection at 0. There is not a point of inflection at 1, because f double prime, this function here, will not change sign at 1 because of the even power of that factor, the even multiplicity. And then it will change at -2. So f is pretty easy to determine, so we can rule out. So definitely f double prime has a point of inflection at 0 and at -2. So we can rule out choices A and B, and then the only distinguishing feature between C and D is whether H has 2 points of inflection or just 1. So you could probably analyze this like algebraically and really figure out how many zeros there are, but you can also just graph it on your calculator and then see if the sign of the function actually changes. And I think that's what I'll do. So I'll type in this function, x times x minus 1 quantity squared times x plus 2 quantity to the third, and then -1, and I'll have a look at the graph. I think I'm going to want to zoom out a bit more. Let me go to zoom standard. Okay, so it looks like the graph changes sign 3 times. I actually do want to zoom in a bit more. Once there, a second time, and then a third time. Oh, 4 times actually. So this thing actually has 1, 2, 3, 4 points of inflection. Okay, So h does not have 2 points of inflection, actually has 4, so the correct answer is C. Okay, guys, so we're going to continue with number 87. They give us this table, and I think I'd just like to copy it onto the page. We have some function, f of x, and we have a table of some values of this function. And I'm just going to copy it here. 9, 4, 0, -3, -5. And in this question, they ask you which of the following statements could be true. It's really a bunch of statements involving whether the first derivative is positive or negative, and also whether the first derivative is increasing or decreasing. What you need to look at to solve this problem is the way in which the values of the function are changing. If you consider the consecutive values of the function, you can see that from this column to this column, the value of the function is decreasing by 5, so going down by 5, and then from here to here it's going down by 4, and then down by 3, and down by 2. Now we can see that over this interval from 1 to 5, the function f is certainly decreasing, right? That's quite clear. The function is decreasing the entire time. Now, because the function is decreasing, that means that its derivative, f prime, must be negative. So certainly f prime is negative. That brings us to either choice A or choice B, where f prime is negative. Now, what distinguishes those two options is whether f prime is increasing or decreasing. What you should notice is that these numbers, while all of them are negative, they're gradually becoming less negative. It seems that as time goes on, perhaps the next step would be actually -1, and then 0, and then finally maybe to +1. At this stage, if the difference between the consecutive values becomes positive, then that would be telling us that the function is actually increasing. So what we can say is that yes, f prime is negative. However, the rate at which the function is decreasing is increasing. In other words, f prime is actually increasing. Because as you can see, eventually the consecutive differences are going to become positive, right? Which means that f prime is eventually going to become positive. If f prime is negative over this region and eventually it's going to become positive, then surely f prime is increasing. So that means it's choice B. Okay. Let's have a look at number 88. It is a question about the equation of the tangent line, it looks like. It says, let f be the function defined by f of x equals natural log of x squared plus 1. Let g be the function defined by g of x equals x to the 5th plus x to the 3rd. The line tangent to the graph of f at x equals 2 is parallel to the line tangent to the graph of g at x equals a, where a is a positive constant. What is the value of a? So here is a picture for number 88 that we could consider. We have two functions, f and g, and we really don't know what they look like. We could graph them with our calculator to see if we wanted, but for right now I'm just going to pretend I know what they look like. So we have x equals 2 right here, and what we know is that the line tangent to the graph of f, let's suppose that this is f, the line tangent to the graph of f at x equals 2, so that's this line right here, that line is supposed to be parallel to the line tangent to the graph of g at x equals a, where a is some positive constant. So maybe a is over here, or Maybe A is over here. I don't really know. But the point is that at some x value A, the tangent line to the graph of G at that value of A is parallel to this tangent line here. So maybe G looks something like this. Okay, and as we can see, the tangent line to G, which would be this thing right here, well, I didn't draw it perfectly, but you know, these two lines should be parallel. And the objective is to find A. Well, we know that these two lines, if they're parallel, then they have the same slope. And to my mind, what we ought to do is figure out the slope of this line right here. And then once we know the slope of this line right here, we'll ask, when is the slope of the tangent line to G the same as the slope that we found here? So let's begin by finding the slope of this line, the line tangent to f at 2. That's going to be given by, of course, just the derivative of f evaluated at 2. So let's find the derivative of f. F prime is going to be 1 over x squared plus 1. Chain rule says multiply by the derivative of the inside function, which would be 2x. So that's the derivative of f, which means that f prime evaluated at 2 would be 4 over 5, so 4/5. So the slope of this line right here is 4/5. Therefore, we know that whatever A is, the slope of the tangent line to G must also be 4/5 at that point. Now, what we want, essentially, is we want G prime of A to be equal to 4/5. Because we want the slope of the tangent line to G to be 4/5, and the slope of the tangent line is G prime, and we want that to happen at A. So we're going to be able to solve this equation for A. That's the idea. So let's go ahead and do that. So let's see. So G is given by the function x to the 5th plus x to the 3rd. So G prime of x would be 5x to the 4th plus 3x squared. And what I have to do now is set this thing equal to 4/5 and solve. This equation is not something that you could reasonably solve algebraically, probably, but the good news is that we can use our calculator to solve it. A number of ways of doing it. Solving this equation here is the same thing as solving the equation 5x to the 4th plus 3x squared minus 4/5 equals 0. And so what I'm going to do is I'm going to punch this expression into my calculator and then find the x-intercept, and that will give me the value of A that we're looking for. So let me just get my calculator here. So I have to first type that function into here. So that's 5x to the 4th plus 3x squared minus 4/5. Okay, looks good. And now I guess I'll graph this thing. Okay, I see a couple of different x-intercepts, but remember that we're looking for the A value, which is a positive constant. A is supposed to be positive. So it's presumably this x-intercept right here that we're interested in. To find it, I'll use the 0 function. So I go to second calc, second option, 0. So left bound, I'm just going to sandwich that 0 between my two bounds. And it says 0.44721, which that's definitely one of the options. That's choice C for the problem, right? Okay, so that's the answer for number 88. Okay, so we are going to move on to number 89, which says the following. Let me actually rotate this so I can make the screen a little bit bigger. Let f be a continuous function for all real numbers. Let g be the function defined by, okay, it's an integral function. If the average rate of change of g on the interval between 2 and 5 is 6, which of the following statements must be true? Okay, there are some statements about the average value of the function, about the derivative of the function, about, I don't really know what that would be, and some other integral. So let's just try and interpret the information that they're giving us. So what do we know? We know that g of x is this integral function given by integral from 1 to x f of t dt. We don't really know what f is, but we know that it's continuous, so okay. They tell us that the average rate of change of g over the interval 2 to 5 is equal to 6. Okay, well, let's think about what that actually means. The average rate of change of g is going to be given by what? It's g of 5 minus g of 2 all over 5 minus 2 has to be equal to 6. Okay. So that is what we're being told. Okay. But maybe we should investigate what this numerator actually is. It's the integral from 1 to 5 f dt minus the integral from 1 to 2 f dt all over 5 minus 2. And that apparently is equal to 6. Well, these two integrals can be combined into a single integral. If you remember the geometric interpretation of these integrals, they're referring to areas. Here's a picture. Maybe this is f. Here's 1, 2, and 5. If you imagine this first integral is the area under the curve from 1 to 5, that's all of this. And then this second integral is the area just from 1 to 2. That's this portion right here. So if you subtract them, what you're left with is the area from 2 to 5. So that numerator can be rewritten as just the integral from 2 to 5 f dt over 5 minus 2. I know that 5 minus 2 is just 3, but I think that I have a feeling that if I leave it unsimplified, then I'll be more able to interpret the meaning of this expression. And that's supposed to be equal to 6. Okay. If you look at this expression, it is in fact the formula for the average value of f over the interval 2 to 5. Okay? Because maybe it would be helpful if I rewrote it. Usually the average value formula, you see it like this: 1 over 5 minus 2 integral 2 to 5 f dt. That's definitely just the average value of f over the interval 2 to 5. Right? You integrate the function over the interval and then you divide by the interval width. That's the average value formula. So this is telling us that the average value of f over the interval 2 to 5 is equal to 6. And that is choice A in the problem, right? So it's actually A. Okay, let's have a look at the next one, number 90. Oh, we've got these theoretical type questions. I do like these. So for any function f, which of the following statements must be true? Okay, so there's really no constraints on f here, any function f. If f is defined at x equals a, then the limit as x approaches a of f of x has to be equal to f of a. Is that always true no matter what the function f is? You might recognize this condition. It's actually the formal definition of continuity at a, right? We say that, a function is continuous at a if the limit as x approaches a is equal to the value of the function at a. Well, functions are not always continuous, so this statement certainly can't always be true. If you think about a removable discontinuity, for example, this statement certainly will not, in general, hold, right? So a counterexample to, so this is problem number 90, a counterexample to number 1 would be a function with a removable discontinuity like this, right? If this is a, then certainly the two-handed limit is not equal to the value of the function at the point, right? They're two different things. So we can forget about 1. Looking at 2, it says if f is continuous at x equals a, then the limit as x approaches a, f of x is equal to f of a. Okay, that I agree with, because as we just talked about, this condition here is exactly the definition of continuity. So is it always true that if f is continuous, then this statement holds? Yeah, because this statement is precisely what it means to be continuous. So 2 is definitely always true, no matter what function you're talking about. Let's think about 3. Actually, it looks like from that information alone, we can cross off the remaining choices, right? But let's just look at 3 anyway. It says if f is differentiable at x equals a, then the limit as x approaches a, f of x is equal to. That is also true. The reason why is you might remember that differentiability implies continuity. If a function is differentiable at a point, then it is automatically continuous at the point. So since this function is, or if this function is differentiable at a, it is therefore continuous at a, which means this condition must hold, because again, that's what it means to be continuous. So it's both statements 2 and 3, so that would be choice C.